Do we have a test coming up in this class?
No, because we haven't gotten our last one back yet.
But you're going to get it back on Tuesday. So does that change? It's supposed to be next Tuesday. Oh, well, we can't do that because I want to give you at least a week heads up. So, yeah, maybe, 2 Tuesdays. What would that be? What would be a week from next Tuesday? Would be the 25th. And we'll see what we get through with friction in the next couple of classes. All right, so we're talking about friction. And friction's broken up into square threaded screws, belt friction. That's what I have right now. And then bearings. And we're breaking bearings up into journal bearings, and thrust bearings. We're done with square threaded screws, so now we're going on to belt friction. Yes? I don't know yet. It depends. It will either be up through internal loads or up through friction. It depends how quickly we get through the rest of the stuff. Okay, so belt friction. Here's the idea of belt friction. So I want to start by telling you a story about a princess. You don't? Well, that's the lecture I've prepared, so. Okay, this princess's name is, I believe, Rapunzel, if I'm thinking of the right story. And the reason she's sad is because when people visit her in her tower, they hold on to her hair and climb up the wall, and it hurts very badly. Okay, so that would hurt very much. And so what she learned to do, so at first, once upon a time, at first, she did this, but later she learned, this is important. It's sort of like foreshadowing. There's a little post outside her window, like a little pole connected to the window box, perhaps. And she learned to do is stand here. Here's the pole. And instead of letting her hair drop down straight to the prints, she wraps her hair several times around the pole and then down to the prints. This is a different print. This one's more handsome. Now she's happy. That's not why. That's not the only reason why. The reason is, so this prince, well, let's say it's the same prince. That makes all this make more sense. The prince has a weight that applies attention to the hair. And so in this case, the tension is equal to his weight if he's not accelerating. And that's no different than this. The tension here is equal to mg. But in the first case, the tension that she feels up at her head is also equal to mg. And that's a lot of tension to feel on the hairs on your head. In this case, the tension that she feels from her head is less than mg. And the reason that it's less than mg, this effect, no, it's due to belt friction. So the idea is that some of the load that is being applied to the hair here is taken up by the friction wrapping around that hole. Any questions about the idea here? So that's belt friction. And I'm not going to do a derivation for this. It gets pretty involved. But here's how it works. I mean, there is a derivation. We're just not doing it. So if this is the object that the cable is being wrapped around, the belt is being wrapped around, in this case, this is a cross section of the pole. And cable is coming off the pole, say here and here. Let's say this tension is T2. Because of the friction, this tension is something different, T1, and it's less than T2. Then what you have to do is calculate the angle, beta, between the location on the pole or the, I can't think of a name for, but whatever you're wrapping it around, the angle from where the cable leaves at one point to where the cable leaves at the other point, and that has to be measured in radians. And the ratio T2 over T1 is equal to E to the power of mu, that's the coefficient of friction, beta. So mu is the coefficient of friction. Okay, so you get, first of all, let's just sort of orient ourselves to how this works. This is sort of intuition stuff. So first, what if there was no friction? Then the ratio of T2 over T1 is equal to e to the 0, which is 1. And so in the limit, as that coefficient of friction goes to 0, T1 is equal to T2. And then that thing just becomes a pulley if there's no friction. Let's say an ideal pulley. Second, what happens as more of the cable or more of the belt is wrapped around this thing? Beta gets bigger, so you have e to a bigger number. And so the difference between the high tension and the low tension gets bigger and bigger. What happens when you go multiple revolutions around? Like in this picture here, her hair is wrapped, 5 times around the pole. Well, then that's just 2 pi times 5 plus whatever extra little bit to for her hair to come off at a certain part of the pole and for it to leave at a different part of the pole. And so beta can be bigger than 2 pi. Okay, so let's do an example. Let's say that we have this object. It's fixed. In the drawing, it looks like a pulley, but let's say it's fixed. And we want to figure out what's the force F that has to be applied to support a 100 kilogram mass. So what F is required to hold up the mass? And let's say the coefficient of static friction is 0.4. Well, we have this force leaving here. This is the big one. The big force, T2, comes from the 100 kilograms. And this force, F, is the smaller one. Let's call that T1. And then this is the angle beta. So what's beta equal to? Pi, yep. So T2 over F is equal to e to the 0.4 times pi. Question? E to the 0.4 times pi. And so you get, I guess I just solved for f. And so f is equal to 279.2 newtons. What would F be if this wasn't fixed and we didn't have belt friction? This was just a pulley. Yeah, exactly. Yep. 981 newtons for a pulley. So now part B. What if it's the same setup except the cable is wrapped 3 full times around? And it still looks like this. So you still have the 100 kilograms there and the force F there, but this cable goes around 2, 3, over here. Then what's beta in that case? That's right. Any questions about that? So 2 pi, 4 pi, 6 pi, and then one more pi to get over here. Yeah. So T2 over F is equal to E to the 0.4 times 7 pi. And so F is equal to 0.148 newtons. So if you're, like stuck on a ledge mountain climbing out in the wilderness, your friend's falling or whatever, you should do that wrapping thing. It works really well. Okay, makes it a lot easier to hold on to your friend. Okay. That's true. You need to find something to. It doesn't have to be a column, although if it's not round, you got other. Could cut the rope. Yeah. That would really play into right. It would. Yeah, you might want to just bring some kind of column with you mountain climbing. I had forgotten that is so short. That's all I have to say about belt friction. There's not really much to do except just plug numbers into that formula. So then the last stuff we have to get into is bearings. And there are two types of bearings. The first one is journal bearings. And so here's the deal with journal bearings. So there's an axle. There's the bearing. Here's the axle on the other side. And we have forces applied here. And this axle is rotating in the bearing. The direction won't matter for the calculations. And then the thrust bearing you have the rotating object. In contact with a surface like that. The force is going this way, and we're thinking about either it's rotating like that, or we're trying to think about when a rotation like that will start. And in order to figure out which one of these two cases you have, the thing to think about is what's the surface of contact where the friction acts. So in this case, surface of contact is like this. Ooh, that's pretty good. You see that?
Yeah, your kid put that on his fridge.
We have one of those stainless steel fridges. So no magnets. So you can't do that. And then the surface of contact, the friction acts in a thrust bearing on this surface. And you can have, these can be combined. You can have both, like if you had an axle with a flange, and that axle goes through like a hole. So in this case, let's see. These are hard to draw. Okay, so if this was a bearing and this went through the hole, you'd have contact with the round part of the axle on the bottom of that circle, the bottom of that hole. And then you'd also have, that would be the journal bearing friction that would be acting there. And then you'd also have this flange bumped up against the side. And so whatever the size of this flange is, you'd have thrust bearing friction on an area like that. Okay, any questions about what these are? You sort of follow what I'm drawing here. Yeah, so, and then, So this would look like, when this was put together, it would look like one of those pin joints that applies thrust. Okay? Like a pin joint that also prevents motion along the axis. Probably. Ay, ay, ay. That's not how it would look. How would it look? Yes. So this, the axis is still going through that hole, you know, and this thing is still rotating like this. But now you have to have some load pushing the, in order to have thrust bearing friction, you have to have some force P pushing these two into contact. And in order to have journal bearing friction, you have to have forces like this. And so you would have journal bearing friction like so. And you would also have thrust bearing friction there. So this P would cause that thrust bearing friction, and these F's would cause the journal bearing friction. Any other questions? Okay, so first let's do journal bearings. And again, I'm going to go through these derivations, and I want you to be able to derive these formulas, not just use them, you know. Okay, so journal bearings. So let's say that there's some weight, the axle's rotating like this, and there's some weight force causing this friction. I'm going to call the total weight W, and so I'm going to break it up into W over 2 on each side. And now we're going to think about what this looks like. And actually, let me, well, that'll work. Okay, so what does it look like to this guy? A free body diagram of the axle from this guy's view looks like this. So there's the axle. There is a total force. If we're isolating that whole axis, that whole axle, We have 2 of those W over 2, so there's a downward force here of W. And if there was no friction at all, if this was perfectly frictionless, this rotation, you would just have an upward force of W counteracting it. And what that would mean is if you got this thing rotating, it would rotate forever, right? There'd be nothing to slow it down. Newton's second law would just say W equals W. Rotational equation would say no moments about the center, and so this thing wouldn't have anything to slow down rotations. And so from his view, it's rotating like this. What really happens is if you look at there is friction, if you looked at measurements of the total distributed load coming from the contact force between the bearing and the axle, you would see that the net force moves away from the center of the bottom. You know, if it doesn't act directly on the bottom of the axle, it acts over here. That total force is W. That has to be because we know from experience that this axle doesn't have any translational acceleration. But what this does is it means that there's a moment produced. Like if you choose your about point to be the center of this, there's no moment produced by the weight down. But there is a moment produced by the force W acting up from the bearing. And the moment produced there tends to slow down the rotation. And so if this is a distance rho, there's a moment rho times W slowing down that rotation. Or another way to think of that is if you wanted to keep that moving with a constant angular velocity, you'd have to apply a moment in the direction of rotation of rho times W. Okay, so what we have to figure out, we know what that W is. That's the force that's applied. That's the weight of the thing that you're supporting. We just have to figure out a way to calculate what this rho is. So we need to calculate distance rho. Anybody have any questions about where we're going with this? So I'm going to do just a big blown up picture of that axle, and we're going to work through some trigonometry, and we'll be able to figure that out. Okay, so here's the axle now. We have a downward force W there. We have an upward force of W somewhere over here. And that W is made up of a normal force and a friction force. This W is the total contact force. And so that W is made up of, we don't know what it is yet, but we're going to be able to calculate where it is on the circle. We know that it's not at the center because then it would spin forever. No, where it is depends on how much friction you have. So this is the total contact force. You can break it up into a normal force that's perpendicular to wherever that point is. So that's N. And a friction force that's tangent to the circle at that point. That was weird. Okay, so there's double W. That's the contact force. This is N, and this is the friction force. And what's the magnitude of the friction force? Well, if we know the coefficient of friction, this is just equal to mu sub n, mu times N. And these two are perpendicular because the normal force and the friction force are always perpendicular. Okay, and then this is some angle theta. And the reason that we care what that angle theta is that if you continue this line that the normal force follows, it goes to the center of the circle. And this angle here is the same theta as that angle between the up, the vertical upward force and the normal force. And this distance here is what we're trying to calculate. This is the rho that we want. And so if we can figure out what this angle theta is, then rho is just going to be, so if this is the radius of the circle, what's rho going to be once we know theta? It's just SOHCAHTOA. So yeah, r sine theta. Exactly. So rho is equal to r sine theta. We just need theta. And we can get theta from this triangle. So there's theta. This triangle has an opposite side, mu n, an adjacent side, n. The hypotenuse is w. I'm going to write that as square root of n squared plus mu squared n squared square root. And so r sine theta is equal to r times mu n over that big square root thing. And you can simplify that a little bit. Pull the n squareds out of the square root and cancel them with the top, and you get mu r over 1 plus mu squared square root. The moment that this friction provides is that force W times rho, and this is the rho vector. It's not a vector, this is rho. And so the moment, that moment provided by the friction is equal to mu r w over the square root of 1 plus mu squared. Yeah. That. Any questions about that? So the problems I'm going to give you, I'll give you the numbers, and you have to work through that calculation. Let me do one. Okay, so here's an example problem. So here's the bearing and the axle. And let's say there's 4,000 newtons on this side, 4,000 newtons on this side. The coefficient of static friction between the bearing and the axle is 0.05. The coefficient of kinetic friction is 0.02. And the axle has a radius of 3 centimeters, 0.03 meters. So first, what's the M that must be applied to initiate motion, rotation? And then second, what's the M that must be applied to maintain a constant angular velocity? Maintain constant angular velocity. Okay, so there's the axle. We have a total weight force down of 4,000. And then it doesn't matter which side you do this on. We're just calculating magnitudes. The moment always, you could calculate the direction and stuff, but There's nothing surprising. The moment you have to apply is just in the direction of motion. Yes, thank you. So yeah, that's the total weight. And so then we have an upward force of 8,000. Oh, I did that here too. I'm just so used to doing it over on the right. You see what so when I drew this, I said that because of the way I drew the rotation, I said that contact force, the total contact force moves this way, sort of you can think of it, if it's rotating this way, that thing's sort of climbing up the wall of the, force-wise, it's sort of climbing up the wall of the bearing. And then when I went down here to the big picture, I switched over to the direction I'm more used to drawing it. You see what I mean? So if you were confused about that, it's because it doesn't make any sense. That's all. But you can do it on either side. We're just looking for magnitudes. Okay, so that 8,000 Newton force is made up of normal force and a friction force. This is theta and this is theta. So this is n, and this is mu times n. What are we doing? We're trying to figure out the moment that must be applied to initiate motion. We have two coefficients of friction. So if we're talking about this thing being at rest, and we're trying to figure out the moment we have to apply to get it moving, which coefficient do we need to use? Static, yeah. And so this is 0.05 n. And so this triangle, there's theta. We have 0.05 n, n. And so theta, well, SOHCAHTOA says that tangent of theta is equal to 0.05 n over n. And so theta is equal to the inverse tangent of 0.05. Can someone calculate that in degrees? You don't have to do this here, but if you want to, that's fine with me. You could just carry these all through as variables until the end. That's better practice, but you could also just keep 8 decimal points and it all comes out the same in the end, you know. So what do you get for that? 2.86. And then 6 more decimal places? 240. Okay, 24053 degrees. Well, so what we really should do is we should do the thing that I did in the derivation. We know that what we're going to need is sine of theta. And so we should use these values. We know the hypotenuse is n squared plus this squared all square root. And then we know that sine of theta is equal to opposite over hypotenuse. So then we get this expression that we can simplify. You know, like ideally, you shouldn't plug your numbers into your variables until the last step. I don't know. I've just never really cared about that. You'll have classes where the professor will care about that more than life itself. But I've never been that way because I'm just like, just use higher precision and it's all fine, you know. Yeah, you can do that. I think your calculator does it automatically, but you can make it show it to you, you know. It just truncates it. But like in programming languages, you know, like you can choose different precisions on your decimals. All right, anyways, this is theta. And so then the moment is equal to rho times 8,000. Rho is equal to radius of the axle times the sine of this number. You don't really have to keep that many decimal places. Nope. And then times 8,000. And what do you get for that? That seems too high. Because sine of 2.86 degrees is going to be really little times 0.03. Okay. Okay. So 11.9 what? Okay. 11.99. Yeah. Okay. No, I want to make everyone comfortable. Okay. Newton meters. So in order to get this thing moving, you need to apply 11.985 Newton meters. And then for part B, everything's the same except that, so I'll skip the first couple steps, but we have a new triangle. So now the idea is that this thing's already spinning, and we want to know the moment that you have to apply to it to keep it moving with a constant angular velocity. So our normal is n. And our friction force this time uses the kinetic coefficient of friction. So 0.02 n. And so theta this time is the inverse tangent of 0.02. What's that? Okay. Degrees. And then once you find that angle, the moment is W times rho, which is 8,000 times the radius of the axle times the sine of 1.1458 degrees. And what's that? Four point 799 Newton meters. Oh, so multiply that by 5 halves. Does that just come out to? Okay, so I never noticed that before, but all it did was change the moment that you had to apply to it by the ratio of the coefficients of friction. Any questions about that? Okay. Then the last topic is thrust bearings. So I'm going to do this derivation for like a hollow tube that's rotating, and there'll be like an inner radius and an outer radius in the formula. And well, I guess you're not really going to use the formula, but basically you just set that inner radius to 0 if you wanted it to be a solid tube. So here's what we're talking about. We have this hollow tube in contact with the ground. It's rotating this way. That's the direction of the angular velocity. And there's a force downward of P. And we want to know what's the moment required to keep this rotating. And actually, in this case, I think it's probably more likely that what you'd be doing, the math is basically the same, but it's more likely that you'd think of this as what's the maximum moment you could apply without initiating rotation. Okay, so for this derivation, what we're going to do is think about the surface of contact. So this is the contact between the tube and the ground. And there's a total normal force that's equal to P. So the total normal force is P, and that P is spread uniformly over that surface area. And so the first thing we're going to do is just figure out what's the normal force per unit of area, because that's uniform. So we're just going to figure out the pressure. So the pressure is P over the area, which is P over pi times the quantity I'll call this radius R outer, big R sub O, and this radius R inner, big R sub I. So the area of that thing is pi times the quantity r outer squared minus r inner squared. And what we want to do is we want to assume that every point is acted on by this pressure, you know, and then at every point we want to see what that pressure, what kind of moment that that produces. Okay, here's what we want to do. Each element here, think of like a small element of area. There's a normal force at that small element of area that's equal to this pressure times whatever that tiny little area is, right? That's its share of the normal force. Does that idea make sense? And then once you have that normal force, we're going to assume that the friction force of that little piece of area is the coefficient times that little its share of normal force. Okay? And then based on how far that friction force, now that friction force is always like tangent to the circular path that it would follow around here. I'll draw that better. But, and so that friction force also produces some share of the moment, you know, because it's a force that's perpendicular to the line between the center of this circle to that element of area. And so for that little piece of area, the friction force produces a moment. And then once we have that little share of the moment, we're just going to integrate, add up all those little shares of moment to get the total moment. That's the idea. The last thing that we have left to do is, I think I mentioned this in all my classes, you know, like anytime you have an integral definition of something, the key step in getting that integral definition to work is coming up with the right way to break up whatever you're integrating over. You know, if you break it up in a nice way, it'll be easy to do. If you break it up in the wrong way, it'll be impossible or at least really hard. You know? So what we want to do here is we want to break up this total area into infinitesimal areas. That's supposed to be a circle. Damn it. Okay. So say that's an infinitesimally thin strip. That's a distance r from the center, lowercase r, okay? And it has a thickness of dr. And for that strip, we're going to use the pressure that we just calculated to figure out the share of the normal force on that strip. Then we'll use that to figure out the share of the friction force on that strip. Then since every point on that strip is the same distance from the center, we can figure out the share of the moment on that strip, and then we can integrate. So let's think of this as the first step. First, we calculate that pressure. Second, we're going to calculate the share of the normal force on that strip. I'll call that dn, you know, d normal. And that's equal to the pressure times the increment of area. So that's P over pi times the quantity r outer squared minus r inner squared. There's the pressure. Times dA. And we can come up with an expression for dA. if we think of taking that strip, so if it was easy to integrate over the variable a, we could just leave it as dA, but it's not going to be. We want to integrate over this lowercase r. So we'd like to represent the area of that infinitesimal strip in terms of that lowercase r. And we can do that if we imagine unhooking this at some point, breaking it apart, and stretching it out into a long rectangle. Then that little bit of area is equal to the length, which is the circumference of that circle, 2 pi r, times the thickness, which is dr. So this now is equal to p over pi times the quantity r outer squared minus r inner squared times dA, which is 2 pi r dr. You do get the 2 pi's to cancel. And so now we're at p r dr over big R outer squared minus big R inner squared. So what's the difference between big R's and little r? Does that make sense? That's right. The little r is the variable. So the little r tells us which of these infinitesimal strips we're talking about. The big R is a fixed parameter that just has to do with the size of that tube. Okay, well, if this is the increment of normal force, then the increment of friction force is just equal to, so I'll call it dF friction is just equal to mu d normal. And so that's equal to P mu little r dr over r outer squared minus r inner squared. And then the last thing we have to do is, if that friction force, so notice that friction force, the share of friction force is happening at all of these places inside this ring, but all of them are tangent to the path. Let me stand right in front of it now. So all of those friction forces are tangent to that circle, which means that they're all perpendicular to the line from where that force is applied to the center. And so the moment produced by that friction force is just equal to little r times that friction force. You don't have to understand that, just do it. Yeah. If you want to understand it, I can talk to you about it, but you don't have to. But so then the increment of moment is just equal to r times the increment of friction force, which is p times mu times r squared dr over r outer squared minus r inner squared. And then the last thing we have to do is just integrate. The total moment is just equal to the integral of those little moments. So m is equal to the integral of p mu r squared dr over the quantity r outer squared minus r inner squared. And then we just have to choose the boundaries. What are the boundaries of little r for this integration? Yeah, r inner to r outer. Yep, exactly. And so you end up with p mu r cubed over 3 times the quantity r outer squared minus r inner squared, evaluated from r inner to r outer. I am missing a 2. Oh, I threw away that 2 and I shouldn't have. See this 2 up here in the circumference? That needs to go all the way through. So there's 2's on every one of these. And so anyways, final moment is equal to 2 times P times mu times the quantity r outer cubed minus r inner cubed divided by 3 times the quantity r outer squared minus r inner squared. And wouldn't you just bet everything you own that there's some way to simplify this over this? But there's not. Any questions about that? I'll do an example or two of this, but basically what you're going to need to be able to do on a test is just remember how to go through these steps where there's numbers, and I'll give you numbers instead of all these constants. And I think you'll find it's useful to just remember, like, okay, first you do the pressure, then from there you figure out the part of the normal, then you go to the part of the friction, then you go to the part of the moment, then you integrate. This is the longest, most tedious derivation of all of them, but once you get used, like once you have those steps in your head, nothing's really that hard to understand. I don't think it's just a lot of steps. Okay, that's all.